let me introduce myself first. My name is Andrew Swan, and I'll be co-hosting this presentation session with Will Wong. And I will invite our first speaker, Samyak Surti from UC Berkeley. Samyak is a rising senior studying CS and physics, and he'll be presenting on quantum LDPC codes. And Samyak, please take it away. And let me start the recording in 3, 2, 1.
All right, so yeah, hey everyone. Thank you, Andres, for introducing me. And yeah, so I don't have much time, so I'll jump right into it. So I'll be talking about quantum low-density parity check codes. And my goal with this talk is to give sort of a sufficient pedagogical overview of what these newer code constructions are. And if you guys are unfamiliar with quantum error correction as a field, I'll try and give an introduction to the best of my abilities. And hopefully I can convince you guys that for the mid to long term, these are very important codes. And if at any point you guys have any questions, just feel free to interrupt me. So let me start by describing the characteristics of a code you may already be familiar with, which is the surface code. So a lot of companies like Google have really been pushing for the surface code architecture from the start, and they're pretty convinced that for the near term, they'll be the prevailing code architecture. And they're probably right. But if we start to look past this noisy intermediate scale era or NISQ era, the surface code is just not going to cut it. So when we look at quantum codes, there are three main parameters that we look at. There's n, which is the number of physical qubits in our system, k, which is the number of logical qubits our code actually encodes. And then from that, we can derive what's called the encoding rate, which is the number of logical qubits we're able to encode for the number of physical qubits in our system. So this would be k over n. And then finally, there's the minimum distance of our code, which is defined as the minimum weight Pauli error that you would need to map one state of our code to another. So naturally, if we want more error resilience, we'd like our codes to have greater distance. So with these parameters, let's explain the surface code statistics. So if we have a 2D square lattice, which is typically what the surface code is defined on, then asymptotically, as our lattice grows in size, the encoding rate of our code will actually go to 0. And the reason for this is the encoding, the surface code only encodes one logical qubit. So if we have a lattice that's say of size 10,000 qubits, then at best we would be able to encode only a constant number of logical qubits. And although these logical qubits will be very good and error resilient, again, there's only a constant number of them, and that's not very useful. If we want to do universal fault-tolerant quantum computing, we need to have the ability to encode more logical qubits. Additionally, this encoding rate of square root of n isn't that great. So if we compare this surface code to these new quantum low-density parity check codes, it's a bit of a mouthful to say, but these newest constructions completely forgive that. So instead of a diminishing encoding rate, we actually have a rate that stays constant with the number of physical qubits in our system. So instead of having a rate that goes as 1 over n, we have a rate that grows as theta of 1. So given, let's say, again, this 10,000 qubit system that we saw from before, a constant fraction of these qubits can be encoded as the logical qubits. And there's a drastic improvement over the surface code. And additionally, if we look at our distance, instead of having a distance of square root of n, we can have a code distance of n over log n, which is also significantly better. So we have two major improvements we see here. There's one in the rate and the second in the distance of our code. And unlike the surface code's nice sort of wait for local checks, the quantum LDPC code checks are pretty spread out. I'll go into what this means later on. And this will only come to fruition when we have devices that have all-to-all connectivity, rather than some of the devices we have right now that have mainly local connectivity. Okay, so now I'll go into sort of stepping back and seeing what actually is this quantum error correction encoding and decoding loop, and what does it really mean? So say we have, for our state of our physical system, we have some state psi, and we'd like to first encode psi in terms of the code we've chosen. And I'll elaborate on what this means. So let's say we perform some noisy computations. So every time we apply a logical gate, there's some noise that follows this that can be modeled by some type of noise channel. And following this, we perform some measurements in our system to check, okay, are we actually in the state that we want to be every time we're applying these logical operations? And these syndrome measurements that we perform here tell us whether or not we're in the state that we want to be. Then taking this information we get from the syndrome measurement step, we pass it on to our decoder, and our decoder basically tells us, okay, if there are any errors, what's the right correction operator we have to apply to our system to get it back to the state that we want it to be. So the idea is that we have these four main components to this error correction pathway, and in general, the goal is to optimize the efficiency of this pathway. How fast can we make each of these steps? We want to make sure that we can perform our encoding quickly, perform measurements quickly, and most importantly, we want to be able to decode any errors that occur quickly. So I'm going to quickly give sort of a prototypical example of some quantum error correcting codes that some of you may already be familiar with. So first, there's a 3-qubit repetition code. And as for intuition, we sort of draw from classical error correction and generalize it to quantum error correction. So in the classical regime, we would encode, let's say, a single bit as 3 bits, and likewise, in the quantum regime, we would encode a single qubit as 3 qubits. And what this allows us to do is that if there's an error that occurs on one of these qubits, we can perform these parity checks, which is shown here by this matrix, where we can multiply this matrix to the state of our system and determine adjacent pairs of qubits have the right or same parity. And if they don't, then that signifies that there is an error on our system. And essentially what these bit flip codes and phase flip codes allow us to do is to correct any single bit flip or phase flip error that occurs in our system. So by applying these checks, we can see, okay, there must be an error on the first 2 qubits, or there must be an error on the second 2 qubits. And based on this information, we can determine what's the correct correction operator to apply and return ourselves to the right state. But as you might know, these only correct bit flip and phase flip errors individually. And as we know on quantum devices, we can also have a combination of the two, or bit flip and phase flip errors, or what are more commonly known as Y errors. And that's where this 9-qubit Shor code comes into the picture, where we can correct for both of these errors at the same time. And it's sort of a concatenation of these bit flip and phase flip error correcting codes, where we first do an encoding using the bit flip error correcting code, and then we do an encoding using the phase flip error correcting code. And then in totality, we end up with this 9-qubit error correcting code. Okay, so now I want to sort of talk about how can I put these codes under this umbrella term of stabilizer codes. So we define a quantum state that is a +1 eigenstate of a Pauli operator S as the stabilizer state of S. And this notion comes from the fact that S stabilizes the state psi. And recall that Pauli operators have +1 and -1 eigenvalues. Thus, there also exist states phi that are destabilized by S, meaning that when S is applied to a state phi, it yields negative phi. So using the existence of these operator state pairs, where the operator is stabilizing the state, we can define a stabilizer code as one that has a set of stabilizer measurement checks S, and whose code space C, which is a set of all allowable and acceptable states, is a simultaneous +1 eigenspace of S. And that is, for all states phi and C, and all operators S and S, S stabilizes C. However, if psi is not in C, then there must exist some S and S that S applied to psi yields negative psi. Again, this is due to the fact that Pauli operators essentially are splitting the Hilbert space into eigenspaces, one corresponding to eigenvalue of +1 and another corresponding to eigenvalue of -1. So essentially what happens here is that the problem of error detection is reduced to simply applying these operators and checking, okay, are we getting a +1 or a -1 eigenstate? If it's a -1 eigenstate, then we know that for at least one of these stabilizer checks, that there is an error occurring. And this can tell you, one, like where in our system the error is occurring, and also what kind of error is occurring. Is it a bit flip error, or is it a phase flip error, and things of that nature. And then as such, we can define the Hilbert space of our system as this direct sum of our code space, which again is the set of all allowable states, and this orthogonal component, which is the set of all states that are the -1 eigenstate of at least one of our stabilizer checks. So, okay, so I've given some intuition as to what these stabilizer codes are. Now I sort of want to talk about what are called these Calderbank-Shor-Steen codes and how they're constructed. To further abstract out how these codes are constructed, let's think back to the types of errors we have to correct for quantum devices. So we have two fundamental types of errors. We have bit flip errors and phase flip errors. So one naive way we might do this is, why don't we select two classical codes and we sort of arbitrarily say, okay, this classical code will correct X errors and this other one will correct Z errors. And the CSS construction does exactly this. And essentially what we do is we select two classical codes whose parity check matrices. So these are our parity check matrices where we apply them to our state and we get out a bit string. If we have a 0 in our bit string, that tells us that stabilizer check was satisfied. If it's a 1, that means that it was not satisfied. So what we can do is we can take this, the parity check matrices for these classical codes such that they satisfy this orthogonality condition where hx multiplied by the transpose of hz transpose is equal to 0. And when I say 0 here, I mean that all these operations are being done mod 2. So if I were to multiply these matrices and I get a bit string, or I get a matrix of all zeros, then we know that this orthogonality condition has been satisfied. And therefore, we can sort of construct quantum codes by taking two classical codes that meet this condition. But the issue with this is that it's kind of annoying to find classical codes that satisfy this condition. So ideally, what we want to do is find a way to get around this and create quantum codes by just picking two random classical codes without having to cherry pick ones that meet this orthogonality condition. So I know I haven't really gotten to the quantum LDPC codes yet. I'm getting there. But one important thing that I want to discuss before we get to that is this constant overhead fault tolerant theorem. So there's something that's called a threshold theorem. And what it says is that if we have asymptotically good quantum error correcting codes, and asymptotically good here references how good the encoding rate and the minimum distance of our code are, then we can achieve physical error rates that are below a constant valued threshold. What this means is that if our quantum device is experiencing physical error rate E, let's say, and our code offers some threshold to our error T, as long as E is less than T, then we're able to arbitrarily suppress errors that our device experiences. And although it's been shown that the surface code is capable of achieving some of the highest thresholds, there is still one glaring problem. And the problem is that to achieve this type of fault tolerance, the qubit overhead is just too high. And our hope is that this can be accomplished with a much lower qubit overhead. So in response to these concerns, Gottesman proposed that if we use asymptotically good quantum low density parity check codes, that we can achieve our constant error rate falling below the prescribed threshold while also maintaining a constant overhead in the number of qubits, as opposed to an arbitrarily large number of qubits. So this is the main fact that makes quantum LDPC codes interesting. So if there's anything you want to take away from this talk, it's the fact that these quantum LDPC codes, they offer us a constant threshold due to the fact that they're able to encode a constant fraction of their physical qubits as logical qubits, and they have code distance that's almost linear in the number of qubits, almost linear in the number of qubits. So this is the most important part, is that we can achieve these high thresholds with much less qubit overhead. And that's why if we look past the NISQ era, it makes sense to have this as codes that are useful in the mid to long term. So how are these quantum LDPC codes actually structured? So again, I'll go back to the name. These codes are called low density because the X and Z parity checks for these codes have a bounded number of ones in each row and column. So if we go back to these parity check matrices, the ones for quantum LDPC codes, if you look at each of the rows and each of the columns for these parity check matrices, they have a bounded number of ones. More precisely, each qubit is involved in at most a constant number of parity checks, and each parity check involves at most a constant number of qubits. So if we look at these parity checks, in the case of this 9-qubit code, we see that in each row, there's at most one, and each column, there's at most two ones. So in this case, you can also think of this as, for this particular parity check matrix, if you set our constant value to 2, then we see that every row and column has less than some bounded number of ones. And this is sort of the defining characteristic of these quantum LDPC codes. And the primary sort of advantage over the CSS construction I'd mentioned before is that when we construct these codes, we don't need to choose classical codes that meet the orthogonality condition prior to the construction. We can take arbitrary classical codes and combine them together in a way that this orthogonality condition ends up being met. So let's take a look at what this looks like. So first, we can sort of look at these codes visually. If we have a classical LDPC code, we can describe it with what's called a Tanner graph. And this Tanner graph basically tells us these checks are being performed on these bits over here. So on the right here, we can think of these as our stabilizer checks, and our left, we can think of these as our qubits. So in the quantum LDPC code case, we have our qubits in the middle, and then we have our X and Z checks on either side. So these nodes on the left and right of the graph are our stabilizer measurement checks, and edges going to these qubits basically tell us which qubits are involved with which checks. And the idea is that there will be a constant, there will be a bounded number of edges going from each check to the qubits, and each qubit will be involved with a constant number of checks. So for example, here, this particular check has 3 qubits involved, and then this qubit is involved in 2 checks. So we can use this Tanner graph picture in order to visualize these quantum LDPC codes. So okay, I'm going to go over this pretty quickly. I don't want to go too much into the nitty-gritty details, but I will look at this image instead of all this mathy description. So let's say we have 2 classical codes, again, that are described by these Tanner graphs. What we can do to construct a quantum LDPC code is we can take what's called a Cartesian graph product. And essentially what that does is that if we take 2 graphs, then we can combine them together in a way that we end up with a Tanner graph. It'll be a Tanner graph that represents the quantum code. So if we have one code here, let's say this one is for our X checks, and this code here is for our Z checks, taking the Cartesian graph product, we can then label our edges and our vertices of our new graph in such a way that we end up with a tripartite graph where we have our qubits, nodes corresponding to our X checks, and then nodes corresponding to our Z checks. And if we do this in terms of our parity check matrices, we can construct them using these formulae down here. And if we want to visualize this, we can actually construct the surface code using this formalism of the hypergraph product, where we take one classical repetition code. So there's not a repetition code, but a cyclic code. And the only difference between this and a repetition code is that for a repetition code, we would have 2 checks here going to these, going to the first 2 qubits, and we have a second check here going to these second 2 qubits. The only difference is with a cyclic code, we add 1 more check so that we have a check going to the first and the third qubit. So you can sort of think of it as a circle, and you put 3 dots on the circle. So your one check involves the first 2, second check involves the second 2, and then the last check involves the last and the third qubits.
Hey, Samyak, sorry for the interruption. We're a bit out of time. Can you wrap up?
Yeah. Okay, so I'll just wrap up with this last point. So essentially, you can take the Cartesian graph product of these Tanner graphs corresponding to these cyclic codes, and that'll actually give you the surface code. I won't go into this one. There's a second type of construction called the homological product code. But in general, there's a lot of work being done in this field. There are a lot of different types of quantum LDPC code constructions that are constantly trying to push the boundaries of the encoding rate and the minimum distance. But the philosophy sort of remains the same of taking the products of two classical codes. So yeah, I will call it there. I didn't get a chance to go into the decoding problem, but yeah, I'll just call it there.
Thank you so much. I think we actually ran out of time to have questions, so
Yeah,
apologies on that. Okay, I guess we'll just go into the next presentation, if that's okay with folks. So the next presentation will be from UC Davis with presenters Zbynka and Liam. I apologize if I'm reading the name wrong. Please go ahead and take over, and yeah, I will give you a warning when it's 15 minutes.
All right. Hello. My name is Liam Hofmann.
And I'm Zbynka Kekula.
And we're part of the Quantum Computing Club at UC Davis. We're presenting an educational tool that we've developed to teach basic quantum computing principles to people who might not have a physics or STEM background. So let's get started. So one of the major problems we have when trying to introduce people to quantum computing is that you need to already know some physics if you want to really understand what quantum computing is. And there's a very high barrier to entry in that regard. So our mission is to make quantum computing more easily accessible to people with little to no knowledge. And we think one of the best ways to do that is through gamification. So that's why we've created a game that we're calling Blackjack Q, which is an open source game that gives a quantum spin to the classic game of blackjack. It's fun to play while also teaching quantum computing principles. Blackjack Q is first and foremost designed to be used as an educational tool to supplement a lesson or demonstration, and it focuses on teaching the concepts of superposition and entanglement on a basic level, with different quantum states being represented as card values and suits. If players understand how to effectively utilize entanglement to their benefit, they can turn classical blackjack, which is a game that's rigged in favor of the dealer, into one where the player actually has a better chance of winning. This can be used to introduce players to the effectiveness of quantum computing. It can be difficult to grasp how using probabilities can help at all with regards to solving problems. And by setting up a scenario where we can effectively utilize these principles to game the odds, this allows players to understand their effectiveness.
So 2 important concepts we decided to show in our game are superposition and entanglement, since they're both basic properties of quantum computing. So if you recall the definitions of superposition and entanglement, superposition is the ability of a quantum system to be multiple states simultaneously, and entanglement is objects such as particles share a single quantum state. And so how are we teaching these concepts? So the concepts of blackjack are implemented in this game to get general audiences familiarized. So we have them shown analytically through card playing. So superposition is shown through cards being dealt in a superposition of 2 states. You will see superposed cards in this game where they could be either 1 or 2 values or states. So this is in collapse to a classical card. And entanglement is shown when players have an option to entangle 2 superposed cards, which can be very helpful in increasing their chance of victory. And so classical blackjack and blackjack Q. So if you're not familiar with classical blackjack, there's 2 ways to, there's 2 things you can do in it. So you can hit or stand. And so hit is when you get another card. You're able to hit until you go over 21. And stand is when you keep your current cards and do nothing, you cannot receive more cards. So in classical blackjack, you play against the dealer and other players to see who gets closest to 21 without going over. And then in this game, aces count for either 1 or 11. And then if both the dealer and player go over 21, the one with the highest value of cards wins the game. As noted in the picture, players start with 2 cards, as does the dealer. And Blackjack Q, one thing to notice, as you see here on the right, we have 2 cards which are superposed. So this card is a 10 or a 5, and the one on the right is a 3 or an ace. So this is a start screen with what you see when you start our game. So you see the dealer and the player and the cards they have. So here we start off with the superposed card, which is a 4 or a king. So the player starts here, so they have either 50% chance of either 4 or king. So just in classical, the player can choose to hit or stand. And once you choose hit, you now have the option to collapse or entangle. So collapse. As you can see here, we start with the two superposed cards, and collapsing chooses one value of the superposed card randomly. So collapse only does that for one card at a time. So in this case, we end up with either a 5 or a 7. And so after hitting collapse, we end up with a 5. And now we have the option to either hit or stand. And so I select hit again. And so here, continuing from the last side after hitting, we are faced with the 5, a jack ace, or an 8 king. So we select entangle. After entangling, we're met with these 2 rows of cards, so we can get a combination of the 2 cards from the first row or the combination of the cards from the second row. After that, we can get either a 5, a jack 8, which is 23, or a 5 plus ace plus king, which is 16. To select 2 cards from the 4, I select stand, and I end up with the first row, which is a jack and an 8. I am unable to select more cards, and then the game ends.
So let's look at how to use the tools that were given to effectively win the game. So this is a situation that you might come across in a game. The 2 has already been collapsed, and there are 2 quantum cards remaining. One in a superposition of ace and 10, and the other in a superposition of 3 and 9. So if you're in this situation, what do? You probably shouldn't draw any new cards, but the question is whether to collapse each card separately or entangle the cards and then collapse the top and bottom quantum states together. Well, let's think about the odds. Remember that aces are worth 1 or 11, depending on whether they cause the player to bust or not. If we choose to collapse these states separately, there's a 25% chance we get a 21, that's the 10 and the 9. There's a 25% chance we get a 16, that's the ace and the 3. There's a 25% chance that we get a 15, that is going to be a 10, 3, 2. And there is a 25% chance that we get a 12, which is the ace and the 9. And remember, the ace is 1 here, because if it was 11, that would be 2 plus 11 plus 9, which would be 22. So it has to count as a 1, and we get 12. So let's try to entangle these cards and see what happens. So actually what we found is that it's a much better option to entangle, because now we have a 50% chance of 21 and a 50% chance of 16. We've removed the 2 smaller options entirely, and we've doubled the chance that we can get 21. This goes to show that by using superposition and entanglement, we're able to gain an advantage over the dealer. So we debuted the game in paper form during UC Davis's Picnic Day, which is a massive annual event that draws 70,000 visitors to campus. And pictured here is Tim, who's the president of quantum computing at Davis, giving a demonstration of the game to spectators. 83 people played and finished at least 1 game of Blackjack Q, and 43 people won. But more importantly, we were able to educate many people on quantum computing principles through the use of this game. The game is also open source, so educators can continue to use it to teach quantum computing principles if they would like to. So we had decided to give a little bit of demonstration. I can share my screen now to give a quick run through of the game. And then after that, you guys should be able to play it yourselves. So let's.
I'll put the link in the chat.
Yeah. Okay. Here we go. And yeah, also have to make it full screen. It does not work if it's not full screen, unfortunately. So we can also make this kind of a audience. We can give audience suggestions for what to do. If you guys want to do that, you can either put it in the chat, or you can just unmute yourself. Yeah. So let's see. We see that the dealer here has 12, and the player has either 6 or a 4 on this side, and a 4 or a 3 on this side. So do you guys think that we should collapse this card first, or should we entangle the 6 and the 4, or the 4 and the 3? Let's see. And if you guys don't want to, if no one really feels comfortable unmuting, then that's fine.
You can type in the chat, first or second, and the first will be for the collapse, and the second will be entangle if you guys want.
Okay, so collapse. All right,
A lot
yeah,
of people are saying
cool.
collapse.
At least 2 people say that, so we can try
Yes.
that. Let's collapse this here. And so we've got a 4 and then a quantum card here. I'm going to just go on a limb and say that we should probably hit, because if we stand, we're automatically losing. So let's hit and see what we get. Ooh, an ace. So let's see what the options are here. So if the ace, let's see, because with this card, we've either got an 8 or a 7. And this, so we're in a pretty good position, that I'd say, because I don't remember if we mentioned this in the presentation before, but the dealer automatically stands if the dealer gets 17. So we want to make it so that we get above that at least. That's generally a pretty good strategy. So let's see, what do you guys think that we should do in that regard? Do you think we should hit or no, not hit, or collapse or entangle? Let's see, so I'm seeing entangle. Well, let's see what would happen if we did that. If we entangle, we get a ace 4 4 or a 9 3 4. So that gives us this is going to be 19, 4 plus 11 plus 4, that's 19, or 3 plus 9 plus 4, which is going to be 16. And what happens, are any of like these diagonal possibilities, or any of those a good idea? Let's see. So 4 and 9 gives us 13, plus 4 is 17, and ace and 3, that would give us 14, plus 4 is 18. So we've got either 14 or 16 if we choose to entangle, or 17 or 18 if we choose to collapse separately. I believe I'm doing that math right. Well, let's see. It depends on whether we're trying to play it risky or trying to play it safe. We can try to do it risky, see if we can get the 19. So let's collapse, or not, sorry, no, not collapse, entangle. So we probably should not hit in this situation, because, well, technically we could. If we want to say that we're going to get the top one and 19 isn't enough for us, we want to get 20 or 21, we can hit, and then hopefully we get a card that collapses. Either we get a ace or a 2, or this ace will collapse to a 1, and then we can hopefully get like a 10 or something, which actually would bring us right back to where we started, which probably would not be a good idea. So yeah, I'm going to say that we stand here and see what happens. So unfortunately, the dealer did manage to get 19. So that's win some, you lose some. But I think like we did play it risky. But yeah, I think that goes to show that at least I think that it's a pretty fun game. And I'll stop the share here. Yeah. So rip us. But so I think so Zbynka can put the link in the chat, and you guys can try it out for yourself, or if you have any questions for us, you can ask us.
Yeah, we're very happy to take any questions or comments.
Yeah, and since I think we're probably a little bit past where we're supposed to be, so if there's no time for questions, then that's fine. Also, this is a continued work in progress. If you have any suggestions for the game, I would be happy to hear those as well.
Thank you for the amazing presentation. This is really cool. I think we have time for maybe one question. Yeah, anyone want to take the shot? If not, then
can I ask something?
Go ahead.
When you were first trying to like come up with this sort of pedagogical tool, did you think of anything other than Blackjack, and how did you end up landing on Blackjack?
Ooh, yeah. Actually, originally I was, because this was kind of the product of a hackathon that the Quantum Computing Club put on. There were a lot of games that we did. Our group ended up doing Blackjack. Originally, I think, let's see, I don't remember exactly what I wanted to do. I think I was thinking about chess, but that would have been quite, like, that would have been very time consuming to do, I think.
Yeah, you only had like 3 days, so.
Yeah.
Probably.
Yeah. I'm trying to remember, because there was one that I was like, thinking of doing, but I don't remember what it was. But then I think we decided to focus more on Blackjack later. It was chess, also Connect 4, I think, was another idea.
Oh yeah, a lot of other teams did Connect 4, which is also really cool.
Yeah.
But we chose Blackjack because usually like in casinos or like when you play it, like it's really rigged in favor of the dealer. So we thought it would be very good to like have it in favor of the player instead.
Ooh, is there already a quantum chess? Maybe. I don't know. If there is, then I'm glad that we didn't choose that. I looked up quantum blackjack, and from my Google search, it does not look like there is one already. So, yeah.
Thanks for that answer.
Yeah, thank you. And yes, Connect 4 has been solved, but we were trying to use quantum computing principles, like I don't remember exactly what we're going to do, like entanglement and superposition, to make it so it's an unsolved game. Also, Zbynka, did you? Oh wait, no, yes, you did. I didn't see that, but yeah, the link's in the chat if you guys want to play it for yourself.
Thanks again. Maybe we should make a coalition game night sometime using Blackjack. All right, then. Thanks again for the talk. We will move on to the next presentation. Will, would you want to take over?
Yeah, sure. So hello, everyone. I'm Will, and I'm co-hosting this session with Andres. For our first speaker, we have Jeffrey Kwan from UCLA. Jeffrey is a second-year computer science major, and apart from quantum algorithm, he's also interested in natural language processing and computer visions. And today he's going to present on auditing the society impact and viability of near-term quantum algorithms. So let's welcome Jeffrey.
Oh, okay. Can everyone hear me?
Oh, yeah.
Okay. Just before I begin, I'm gonna skip over some like machine learning stuff just because I don't have a lot of time. But in case anyone's like lost, like just ping me on Discord or something, and I'm happy to go over it. Okay, so brief introduction. So TikTok is all around us, right? If you wake up in the morning, you're on TikTok. If you're eating lunch, maybe you're on TikTok. And, even if you're taking a dump, right? Like chances are you're probably on TikTok. So what makes TikTok so Gen Z and what makes Facebook so boomer? To answer this question, we're going to look at something called recommendation systems. So this is a user preference matrix. It basically encodes information about what each user kind of likes and dislikes. So as you can see from this first user, probably likes Harry Potter, doesn't like Memento, and likes The Dark Knight Rises for some reason. And apps really determine what they show their viewers based on things like these, right? So for example, TikTok may have some pretty like relevant categories, and maybe Facebook has, I don't know, whatever from the 2010, which is why it's like pretty outdated, I guess. And this, as you can think, may also create social problems because these kind of determine everything that a user sees, which may cause divisive content. So let's just disregard all the consequences for now, and let's just make it exponentially faster. So we're going to introduce quantum into this, right? And so basically what a quantum recommendation system does is it takes this user matrix and you turn it into a quantum state, and then you can do whatever you want with it. But the problem of turning a user preference matrix into a quantum state requires something called QRAM, which people don't know if it will work or not. There's no scientific consensus on whether this is an implementable technology. But the QGAN promises to demonstrate that QRAM actually works, and that it can load states in polynomial time, which will allow whatever algorithm it's running on to have some kind of quantum advantage. So before I begin the rest of my presentation, here's just a brief overview of what I'm going to be covering. First, I'm going to talk about how QGANs work. Then I'm going to talk about like the experimental setup I did and then I'm going to talk about some results we had, some challenges, and then some future research directions. So just before we begin, so why are we, trying to make something that will enable these kind of societally damaging algorithms like work better? And the answer here is that we want to make sure that, if these algorithms actually show promise, that we know about it first, that we can develop the analysis tools and like the technology needed to understand these algorithms and prevent like any sort of, damage from happening without us even knowing why it's happening. So without further ado, let's go into it. So what a QGAN is, or quantum generative adversarial network is that your goal is to load a quantum state that kind of corresponds with the target probability distribution. And again, you can use this quantum state in other applications, such as the quantum recommendation system I mentioned in the beginning. So, but before that, let's take a backtrack and let's just talk about what a generative adversarial network is. So this is a something that came from classical machine learning. Your goal is you want to generate something. Could be a probability distribution, could be faces, and there's three main components, right? You have some kind of data, you have a generator, and you have a discriminator. And the point of the generator is you want to basically mimic the real data so that the discriminator can't really tell them apart. And the discriminator's job is to call the generator out and tell if like the data is given to it, if it's from the generator or from the real data. And these two models kind of compete with each other in this adversarial fashion, and eventually they get so good that you can actually generate real faces and your discriminator just can't tell them apart. This is called Nash equilibrium, in case you're curious. And I also made like a brief flow chart here just to highlight the concept of it. So you start with the generator, which is a neural network. It outputs some kind of probability distribution. You feed it with the real distribution into the discriminator, which tries to tell them apart. And through optimization, like classical machine learning optimization, you end up with some kind of optimal probability distribution, which you can then use to generate stuff, right? So now let's add the Q into the equation. So there are two setups actually in the literature. One uses a classical discriminator and one uses a quantum one. And for the purposes of my research, I use the first setup. So same diagram, but let's do it in the quantum way. So we start off with the quantum generator. This spits out a quantum state. You can sample it to get a classical probability distribution, which you can then feed into a classical discriminator with the real probability distribution, and the discriminator tries to tell if it's real or fake. And through a process of classical optimization, you end up with the optimal quantum state, which you can then do whatever you want with it. So that's it for the overview, and let's get into the testing setup. So the objectives of my research is to determine two things. One, how accurate I can kind of like reproduce a QGAN, and secondly, how scalable is it? For accuracy, we're going to use a pretty standard machine learning training process. And in order to evaluate how good it is, we're going to measure the distribution difference in what we generate from the QGAN and like the actual data using something called relative entropy, or also known as KL divergence. As for scalability, I want to investigate how the training time of this QGAN is affected by scaling up the number of qubits. And then we're going to plot this on a log scale, because if it is exponential scaling, you'll see this kind of linear relationship as I've shown on this graph. And if you have, polynomial or like linear, then you'll see like this kind of like it will just asymptotically approach some kind of limit. And for the model architectures, the generator, I'm just using whatever is in the paper, which is a series of Y rotations followed by some entangling blocks full of controlled Z's. And then you repeat this for some number of layers, which in my case is 2 or 3. And for the discriminator, you just use a very standard fully connected neural network. Here are some other hyperparameters in case you're interested. I'm just going to highlight that I used the range of 2 to 15 qubits, and anything beyond that took way too long to train, so I didn't bother with that. And for the probability distributions I was trying to imitate, there are 3. So you have this triangular one here, you have a log normal one, and you have a bimodal. These were all taken from the paper, so they're pretty much arbitrary choices. As for devices, I used Penny Lane's Jupyter Notebook environment, and this is just some information I printed from it in case anyone's interested. So that's it for the testing setup, and let's get into the results. So firstly, for accuracy, I wasn't actually able to reproduce the results of the paper. Some looked pretty decent. This is basically the real one is the one in purple, and everything else kind of looked like that, which is pretty close. For some reason, this value is super off. But some are, I don't know what happened, and there's stuff like this, which anyways. And even when I pushed up the epoch to the extreme and tried all the optimization methods that the paper mentioned, I didn't really get any concrete results. But on the scalability side, we actually see something interesting. And I think this is actually independent of accuracy. We see that if you scale up the number of qubits, and you plot on the log scale, you see a linear relationship. And what that tells us, right, is that the training time actually scales exponentially with the number of qubits. Although the paper mentions that it uses a quote unquote polynomial number of gates, so polynomial time, the training time itself actually is exponential. And you might be wondering why I didn't run it on a better device in order to for training time. It's because this doesn't actually affect the scaling factor, right? The more you scale the qubits, it's going to scale in this exponential fashion, which is not good if you're thinking about scaling it to the orders of hundreds or even thousands of qubits. So one other challenge I want to mention is something called barren plateaus. So this kind of thing happens when you kind of scale up VQAs. You run into a problem where the cost landscape kind of flattens out and you can't perform any gradient descent, which means that no training can occur, and basically you have an algorithm that will never get to the optimal point. And in practice, this can be detected by tracking the mean and variance of the gradient. And if they vanish kind of exponentially, then we see this phenomenon of barren plateaus. And I think that this may have an effect on why my accuracy wasn't, getting any better. And so some directions for future research is that I can, one, work on improving my accuracy by including two other techniques to mention in a paper that I haven't had time to go over. One is batching number of samples, so using the same parameters a few times, multiple times to generate something, and then using all of that information in one time step to do one step of the iterative process. The second one is using some kind of initialization strategy. And this is thought to also basically eliminate barren plateaus, which may lead to better training. I also want to do a more extensive kind of benchmarking of the scalability by using tweaking some other hyperparameters and seeing if that actually changes anything, and also using GPUs and using other quantum computers and whatever, just to see if the noise or any other factors I haven't considered kind of affects my analysis. Last thing I want to do is investigate barren plateaus itself, and we can do this in two ways. One is through empirical analysis, so just measuring the mean, measuring the gradient, and then seeing if those vanish exponentially. Another way mentioned in literature is to kind of do some kind of mathematical analysis. And in the research we have found, or in the literature, we have found that the ansatz and also the cost function have some kind of role to play in determining whether barren plateaus will actually occur. So in summary, what have we learned today? One, quantum recommendation systems rely on QRAM, which is not widely believed to be implementable. But the QGAN claims to be able to load these quantum states at polynomial time. But through testing how the training time of this QGAN kind of scales to the number of qubits, we found that this was actually exponential. And further, future research directions include kind of investigating some kind of confounding factors that really affect my accuracy and my trainability, and more robust investigation into scalability is also needed. So before I end my presentation, I just want to close off with a few thoughts. So as everybody knows, social media has really infiltrated deep into our everyday lives, right? And we know that AI recommendation systems are already propagating all these divisive content, all this discourse across society. This is an image of, body shaming and all these real social issues that people deal with. But imagine if these algorithms ran even faster, right? But we're lucky that the QGAN isn't that scalable yet. So it's not something that we have to worry about right now. But that doesn't mean we can be complacent, because, some of the other factors that I talked about, maybe if they were able to shrink this scalability issue, then we're going to have a problem on our hands. That's the end of my presentation. Thank you for listening. Any questions?
Yeah, I actually have something I wanna ask real quick. So when you're measuring the your training time and how your algorithm scales up, so are you just measuring the part where you classically train the thing, because you're running your circuits and stuff on a simulator? So just checking. Okay, so you're just checking the classical like optimization parts, right?
Well, the thing is, the quantum, like, so the classical optimization also kind of affects the QGAN itself, because you have to kind of update the weights of the QGAN itself as well. And so I'm just measuring the all-in-all time also with the classical discriminator, although the classical discriminator itself shouldn't scale that hard, right? Like the main bottleneck of the entire process is the quantum generator.
Okay.
Thanks.
Mhm.
Yeah. I guess Thomas is next.
And yeah, Tom. Mhm.
Yeah, hi. Thanks for the great talk. I had a question, I guess, pertaining more to just QGANs in general. Regular GANs have that sort of known problem of mode collapse, where basically the generator just gets really good at generating one particular thing, and not like the full diverse kind of phase space. Is that alleviated in QGANs because of like more randomness? I don't know if you know anything about that. That just would be very interesting to hear.
That's a good point, actually, that I didn't really consider. But like for the purposes of this like specific thing, where I'm literally just training on like a single distribution. So like I did each of these. Sorry, where is it? Yeah, each of these separately. So like there's only one mode, so there's nothing to collapse on.
Gotcha. All right. Well, thank you.
And Andres?
Hi, thank you for the presentation. Yeah, I had a question on the scaling as well. So I was wondering if you've studied if the scaling is really from the number of qubits, or was it from the number of trainable parameters?
Right. Well, no, but I think the number of trainable parameters itself like scales polynomial because of I implemented architecture in the paper. I will investigate this, actually. That's a good point. Thank you. But the number of parameters in the quantum GAN itself should be scaling polynomially, but the training time itself is actually scaling, you know, in an exponential fashion. But like others have mentioned, I didn't actually consider the classical discriminator, and I think if I do some research to kind of confirm that, that would be pretty helpful, actually.
All right, thank you so much.
Yeah.
Okay. I do think we have like maybe time for one more question, if anyone has any questions. Okay, then I guess we can move on to the next presentation. Let's again thanks Jeffrey for the wonderful presentation. Yeah. Okay, so for our next presentation, we have Diptanshu, Rohit, Stewart, and Arya from UC Irvine. Sorry for any name pronunciations. And they're going to present variational quantum convolutional convolutionary neural network for image recognition to determine steering angle for autonomous vehicles. So let's welcome our speakers.
Could you guys see our screen?
Oh, yeah.
Okay. All right. So we'll get started.
Hello, everyone. We are Quantum Computing at UCI, and today we will be presenting our project on implementing a variational quantum convolutional neural network for image recognition to determine steering angles for self-driving cars. So autonomous cars, such as those that Tesla Incorporated builds, have revolutionized the automotive industry by leveraging complex deep neural networks. These networks enable the cars to make instantaneous decisions based on real-time data collected from various sensors installed on the vehicle. This advanced technology allows autonomous cars to navigate roads, detect obstacles, and respond to traffic situations without human intervention. One major feature of autonomous driving systems is the autopilot, the ability to control the steering angle of the vehicle relative to the road. Convolutional neural networks, CNNs, are particularly well suited for analyzing image data, making them excellent for predicting steering angles based on visual input. A powerful CNN model can ensure that the car stays on the correct path and follows the intended trajectory. To build better self-driving models, we either need billions of miles of driving data or more complex models that train faster or lesser data. In this project, we propose implementing an autopilot feature by constructing a hybrid neural network. This hybrid network combines classical layers inspired by conventional deep learning architectures like CNNs with quantum layers, which incorporate elements of quantum computing. The goal is to leverage the benefits of both classical and quantum approaches to enhance the prediction accuracy of the steering angle using video road data as input. Once the hybrid neural network is developed and functional, we will benchmark it against a fully classical CNN model. This will serve as a reference point for evaluating the performance of our hybrid CNN. By comparing the two models, we can assess whether the hybrid approach offers any significant improvements in terms of accuracy, training speed, or generalization capabilities. Through this project, we aim to push the boundaries of autonomous driving technology and contribute to the development of more efficient and reliable self-driving models.
All right, so now moving on. So the premise is behind this is basically exploring quantum transfer learning methods, and similar to like how variational quantum eigensolvers work. So we know that for a variational quantum eigensolver, it's usually we have like a quantum circuit and like a classical optimizer on the right. So what we essentially do is we transfer these parameters for a set number of iterations or a set number of convergence point till we get some sort of result. And this is usually used, a very classical example is to like approximate the ground state of a molecule or a ground state of a particle. And using the same premise behind that, what we're basically doing is that the quantum side is a variational quantum circuit that we will show in the later slides. And the classical side is going to be our convolutional neural network. So we're going to be using these layers in the deep neural network, and we're going to transfer the weights in the CNN as parameters to the quantum circuits. And then these quantum circuits will essentially augment the classical neural network, and it'll help us find the optimum steering angle based on images from a car's front camera. So we started off by building a CNN with several convolutional layers, max pooling layers, and then and after that, what we're basically doing is that the following one of the output layers will be a variational quantum circuit. So these weights will actually be parameters to the variational quantum circuit, and we're basically doing an entire rotation or an entire transfer learning between the CNN and the variational quantum circuit for a set number of iterations. And then we will evaluate these model performances based on the prediction of the steering angle. So basically, what are variational quantum circuits? So we have these parameters to the quantum circuits gates, and basically the parameter theta is a non-adaptable parameter, and this basically converts classical information into quantum information. And we will see in the example that how these gate parameters usually play in data inputs in basically quantum machine learning. So we have a certain parameter A, and we're using that as the arguments of the gates, and these gates will be arranged in our circuit architecture. And for this following project, we tried out various quantum circuits such as a Hamiltonian variational ansatz and a Hamiltonian efficient ansatz, where we used 4-qubit architectures, and we added various rotational gates because fundamentally it is a steering angle. So we used penny lane rotational angle embedding layers. So now the CNN model.
Yeah, so the bigger part of the two parts within this, one is the variational quantum side and one is the CNN side, right? So CNN stands for convolutional neural network. So I have an example of a convolutional neural network on the top right, this image here. So CNNs are typically used for image recognition, which is why we have approached them. And we have the images first, and then we take a small window and that we convolute it and make a convolution. Then there's some pooling layers and some convolution layers and a series of them alternating with each other. And then finally we flatten them. That's how we get the flatten function to make the flatten layer. And then we have a bunch of nodes, and then we put them basically together with a fully connected neural network, which is what we call the fully connected layer, or FC. And so that's how we have that's how a typical CNN works. Now, the one that we have implemented is we have an image or an image input. It's a video input. So image input comes with 66 pixels being the height, the 200 pixels being the width, and 3 because 3 is the depth because we're talking about 3 channels, or the red, green, and blue colors, and so those are the channels. And then we have the input layers and the convolutional layers, the flatten, as I said, and then the fully connected. Finally, output is one node because that is the steering wheel that we are trying to predict. And how does the CNN fit in? Well, CNN comes in it's the first step before the VQC, right? Because we have to take in the image as an input, do the convolution, and then pass the parameters to the VQC, where we'll do the training between the classical quantum hybrid architecture, which will then predict the steering wheel.
So here's the variational quantum circuit that we kind of found a little successful, which we will show in the next in the model. So here we applied the RX gates, and these the red ones is the embedded penny lane angle embedding, and then after that we applied more RX gates. But these are some pre-trained angle parameter, pre-trained weights that we found from the CNN. And then after that, we applied a couple C0 gates, and then more RX and RY rotational gates. So these are, except this is the only one which is like predetermined. All of these ones are just like, it would have theta. So this theta value is fundamentally from the CNN, the weights from the CNN. So here's a small demonstration of the quantum model. This is done in Streamlit. So this is the quantum model. It's actually not as good, but let me demonstrate. So as you can see, the steering angle is being controlled by the hybrid quantum classical model, and we see that it's not completely perfect yet. So the steering angle is being dictated by the hybrid architecture we have here. And this is just showing the car. We haven't yet set up a complete testing data set to evaluate the model's performance. So right now we can see that the steering wheel angle is a little too much. So what we would do is our next steps in this project is to play around with the ansatz a little more, play around with more gates, add more layers to see if we could train this quantum model more accurately than the classical counterpart. Yeah, thank you. That's any questions?
I can ask a question. So I was a little confused on how you, well, thanks for the presentation again, first. I was a little confused on how you input the CNN weights into the pre-trained angles for the variational circuit. Could you maybe elaborate more on that?
So you mean these ones?
Yeah, I was wondering like how, because I know CNN probably has a lot more weights than the variational circuit. So I was wondering, how do you do the dimensional matching and etc.?
So we just added more max pooling layers towards the end to reduce the number of weights towards the end of the neural network. So around the last, we added just in this one, we didn't actually include those max pooling layers, but once we added more max pooling layers, you could be able to reduce the number of weights that are outputted. And those weights is what we use as like an initial parameter for the variational quantum model.
I see, thank you.
And just making sure, so on this slide, only these gates in the red box are prefixed parameters, and all the others are the ones that you I guess train, optimize.
Yes.
Yes.
Okay.
Yeah, the first four are the input, and the rest of them are trained. Yes.
Okay. And is there any? Have you tried like different ansatzes and see like how the results compares, like just different kinds of. Yeah. Mm-hmm.
Sorry. Currently, we tried out like this is the most successful ansatz that we got so far, but we have tried more ansatzes and we haven't gotten much results. but that could just be because it was not enough number of rotational gates or not enough number of C0 gates. So this is kind of the whole field of this variational quantum models with CNNs. It's a very experimental field. So it's like we don't have a theoretical basis, a complete theoretical basis on which quantum circuit will perform the best. So it's kind of like, okay, we have a certain amount of variational quantum circuits that are used in approximating a ground state for like a hydrogen molecule. So we are just kind of basing off, okay, if it works really good for this, it should also work good for that. So it's really just testing more and more quantum circuits and then trying to find a theoretical basis on why they're performing well.
Yeah, and the initial parameters, like your prefixed gates, also has like a pretty big effect on, like, you know, how this ansatz is going to converge. So yeah, it's a lot of a lot of things happen. Yeah.
Yeah.
Okay. So perfect. Thanks for the presentation. That was really cool. Do we have any more questions from the audience? And if not, we can move on to the next presentation. Andres, you want to take it from here?
Sure, thank you. So we have the last presentation for this session. We'll welcome Thomas from UC San Diego and talk about more on variational quantum circuits. And Thomas, here we go.
Great, thanks. Hop over to here. Hopefully everybody can see my slides and hear me. We'll go ahead and get started. So the title of my talk is Better Variational Quantum Circuits, Ansatz Optimization Using a Genetic Algorithm. And as we go through, it'll sort of explain more about each of those pieces. And this is kind of a collaboration of work between UC San Diego and Caltech. So why should you care about QML? This is kind of my required thing I need to put at the beginning. Hopefully all of you care about QML because you're here, or at least, you know, in quantum computing, but right now you probably shouldn't just yet. Current quantum machine learning methods, they usually take a lot longer to train. They're more annoying to train. They honestly typically perform worse than classical neural net methods. But, you know, this could change quickly in the next 5 years. You know, things could be radically different. And that's just because the field has only been around for about 10, 15 years. Okay, so quick refresher, what are variational quantum circuits? We kind of just saw a presentation on it, so hopefully I can move a little quickly through this. Really, variational quantum circuits are just a quantum circuit where you have parameterized gates, for example, rotations. In the picture on the upper right, the rotations are those purple boxes, and the parameter that, you know, parameterizes them is the angle of rotation. And then we optimize those gate parameters, usually using something like gradient descent. Variational quantum circuits are one way you can implement quantum ML. The nice thing about them is that they're realizable on current hardware, and they're fairly akin to neural nets. We can kind of understand them as being a kernel method where the high dimensional space that we're projecting into is the Hilbert space of the circuit. The real downside of variational quantum circuits is they have something called the ansatz, which is the circuit layout. And it's a completely unoptimized hyperparameter. So in my head, I think of ansatz as just basically being what gates go where. And in the circuit in the upper right, you know, those purple gates, for example, have those angle parameters that we optimize, but we had to choose to put rotation gates there. And that's true for every gate we put on this quantum circuit. We have to choose to put it in a given location. And if it has a parameter, we can optimize that. So as kind of like a one-line overview, VQCs are the quantum analog of neural nets, but they have this extra sort of constraint coming from the ansatz. And what the ansatz ends up doing is it really restricts us to a small subspace of the Hilbert space, which may or may not contain optimal solutions, or indeed even really near optimal solutions. So the goal of this work is let's find a way to optimize the ansatz so we can better search that problem space for a better solution, and along the way, hopefully characterize the problem space as well. So, okay, you want to optimize an ansatz. How do you go about doing that? Let's talk about maybe some challenges and goals you'd have for such an algorithm. In terms of challenges, it's a discrete optimization problem in a very similar vein to the like unbounded knapsack problem. This can be seen just because the choice of whether or not you put a gate on any given qubit is a discrete choice. You either put one there or you don't. There's no continuous decision there. And this really means that it's hard to use gradient descent for this, which is unfortunate because that's the bread and butter of machine learning. This ansatz optimization is also going to be really slow because it's really nested machine learning. For every given ansatz, in order to determine how good or bad it is, you have to optimize that ansatz. So kind of like the performance of any given trial is itself a machine learning problem. In terms of goals, we want it to search really broadly over the Hilbert space. That's kind of the whole point of doing this. It should be general, so you could apply this to any VQC. And ideally, it would have some kind of qualitative characterization of the problem space. And we decided to do this through kind of a combination of a distance and performance comparison of different ansatz. And in order to do that, we had to figure out a way to determine a distance between two ansatz, and we basically used scikit-learn's t-SNE algorithm, and I'll talk more about that later on. This is an overview of what we chose to do in terms of the ansatz optimization algorithm. We went with a genetic algorithm. That's basically because they are really good for ML in non-differentiable spaces and for really broad exploration. If you've never heard of a genetic algorithm before, it's just a really naive version of evolution. We start out with a population of different ansatz. We then optimize those ansatz in a typical VQC way, and we keep the best performing ones to be parents of the next generation. We then mate those parents by swapping some of their gates. Those become children. We mutate the children by randomly changing some of their gates, and we take those children and move them to the next generation and kind of rinse and repeat until we get good enough results. So to be clear, this genetic algorithm is really the tool that we worked on. This is kind of like the end product of our work. It's not fully done yet, but this is the thing that is the whole point of this talk. From here on, I'm going to be talking about the specific problem we decided to apply our genetic algorithm to. And that's just because in order to showcase its capabilities, we have to actually pick a VQC problem to optimize. So we decided to go with this quantum autoencoder for anomaly detection problem, and that's what I'm going to be talking about now. Okay, so what is the quantum autoencoder for anomaly detection? I'm going to review like super lightning what a neural net autoencoder is, not the detailed math, just kind of abstract concepts, so you can contrast it with the quantum autoencoder. A neural net autoencoder really has this training loop. We compress our input data down to some latent space by basically decreasing the nodes per layer. So if you look at the picture on the right, we start with our input data, which is these green, red, blue kind of images. We compress it down to that latent space, which is the light blue box in the middle. We then decompress the data by increasing the nodes per layer. And then the whole point is we're just trying to minimize the difference between our input data and our output data. And the idea of this is we're trying to think of the latent space as encoding the fundamental representations of our problem. Now, for us, we're doing anomaly detection on a physics data set. So we think of it as a physics, the physics of the problem. And we like to kind of pretend that the autoencoders are directly learning the physics because of that. As much as any ML algorithm really learns something. And the way that we do this is we train our autoencoder on some background data. And then if we want to detect some anomalies, we do that by looking for input data that has a really high reconstruction loss on our test data. And that just means that our autoencoder wasn't very good at reconstructing things. So the physics is different. That's kind of the idea. Now, quantum autoencoders are very similar. The difference is you can't really decrease the nodes per layer in a variational quantum circuit. So what we do instead is we use these swap gates to kind of swap in with some arbitrary other states, that's the orange ones. And we treat that as an effective kind of squashing, an effective compression. The details of why this works are not super important, so I'm going to kind of just skip over this for the interest of time. But the main takeaway of the contrasting between a quantum autoencoder and a regular autoencoder, QAEs are very similar, but they have a fixed number of nodes per layer. And we only actually have to run the encoder block. And if people have questions about why that is, I can talk about it afterwards. Okay, so the QAE is a specific VQC algorithm that we're actually optimizing, or the ansatz of the QAE is what we're optimizing. And the whole goal is that by optimizing this ansatz, we can obtain better anomaly detection performance. Let me give a brief overview of what the data set we're using is. It's this LHC Olympics 2020 data set. This is a particle physics data set. All of this, research is done in a particle physics lab. It's not super important, the details of this. The one thing that is interesting to note for later on is that what we decided to use for this data set is only 3 inputs. And one of those inputs is highly correlated to the other 2. So it's a very simple machine learning problem. And that will become important when we look at the results. So let's do just that. We have here a plot overlaying the AUROC of the kind of best optimized QAE ansatz, as well as the loss with respect to optimization steps. So we can see that, there's this really interesting peak here where the AUROC, which is basically just some accuracy metric, it's saying how well is it doing at finding anomalies. It peaks right when the loss first begins to flatten. And we're not exactly sure why. We tried to use this kind of peaking right when the loss first to flatten as kind of a training criteria or like a stopping criteria. That ended up not working for some kind of complicated reasons. But it's just something interesting to note about this specific problem. The other thing to note is that this is converging really quickly. So one step here is not one epoch. It's not one run through of our full data step. It's actually one gradient step. So it only takes a couple gradient steps for our model to achieve basically the best performance. And we think that is, again, just because of how simple of a problem it is. And then, just some stats, the average over, after we got this best ansatz, we then retrained it in the typical VQC way, just to get some statistics on what its average AUROC and loss were. So we did that 20 times and averaged that, and this is what we got. So it seems to be pretty consistently performing decently well. 0.82 AUROC is not bad at all, especially given how large our data set is. Here is the t-SNE for the full population. Now, t-SNE is essentially a clustering algorithm. What it does is it takes some very high dimensional data, say it was like 100 dimensional, that's basically what our circuits were, and it looks for points that are close to each other in this very high dimensional space. And then it plots them down on a 2D plane and tries to make the relative distances the same. So if points are close to each other in the high dimensional space, they stay close to each other on this low dimensional space. The way that it does it ends up meaning that the actual absolute position of any given point isn't important. That's why both X and Y axis are labeled as AU, arbitrary unit. But the relative distances are important. So points that are close to each other on this plot are circuits that are very similar to each other. And the other thing we did is we color coded it by circuit performance, by the AUROC. And we kind of see this interesting division here, where on the upper right side, there's some worse performing circuits. And in the lower left side, there's some better performing circuits. And it sort of looks like you could draw this line kind of dividing the two, where if a circuit ends up on the upper right, it generally performs a little worse, more like 0.7 AUROC. And if it's on the lower left, it's more like 0.8 or 0.8, 2. I think there's more to be looked into here, certainly, but it's promising that there's something interesting going on. Some final remarks. We have this mostly general method. There's only a few ways that it's not fully general yet. And it's published on PyPy for community use. So if anybody wants to do some ansatz optimization, you're more than welcome to just pip install it and plug it into your other PennyLane code, and it should work great. We also implemented this t-SNE through scikit-learn, which basically just allows us to probe that high dimensional solution space and get a plot that looks like this, so we can kind of get some idea of what our Hilbert space kind of looks like in terms of performance. And we were able to show that there seems to be some sort of family of solutions to this problem. In particular, the lower left part of that t-SNE plot seems to all be pretty good. There's still a lot of next steps. We need to still finish generalizing it. There's some other best practices we need to implement. And really the next big things is that we need to try this on a more complicated problem, and ideally try it on real quantum hardware, because all of this has just been on simulation. So here's a link to my email, as well as the GitHub and PyPy for this project. The QR code also takes you to the GitHub. If you're interested, feel free to reach out to me via email or on the Discord. And I'd be happy to answer any questions now or later on. Thanks.
Okay, maybe I can kick off the questions. I was wondering, for different types of problem, does the genetic algorithm change drastically depending on what's your problem type?
By problem type, do you mean like different loss functions or different?
I was thinking perhaps even different, let's just say different optimization processes.
Yeah, so I'm hesitant to say that it would work regardless of, you know, I'm sure you can come up with an optimization process that would break the code, because you can always do that. But essentially the way it works is it just kind of sits on top of the traditional VQC optimization loop. And the idea when we wrote it is basically that you can write your code how you normally would for your VQC optimization, and then just plug it in directly to this genetic algorithm. And you just have to basically tell it what your circuit looks like in a specific way that it wants. There's like functions that know how to decode it. And you have to tell it how well it did with whatever your metric that you're optimizing for is. And then the genetic algorithm handles the rest. So the idea is that no, it should work regardless of kind of what optimization framework you're using.
Sounds interesting. So essentially, if I want to do, say, like find a ground state energy of Hamiltonian, I can also just use the same algorithm to do the answers.
Yeah. I haven't tested that directly, but yes, the idea is that yes, exactly, you can do that.
Sounds very interesting. Thank you. So there's a question in chat by Skylar. Did you find any commonalities among ansatz in similar cluster in TC?
Yes, that was a really good question. How much did I analyze? I did not look at it as much as you would probably want me to answer your question very rigorously. Generally, the commonalities are that the ones that perform worse, and this is not surprising at all, have a lot fewer parameterized gates. So they'll only have like a few rotations, only maybe 2 or 3. And these are all circuits that have, I think, 6 moments. Just to make it easy, I made it basically a fixed number of moments. And the ones that performed better had more parameterized gates. The other big thing that degraded performance was a lack of C-naughts, which makes sense because C-naughts are the way that we would expect information to be passed from one qubit to another. And if you're thinking of compressing data just from like an information theory standpoint, you would expect that you need to have a way of sending that data from all of your input qubits down to only the ones that you're keeping. And if you don't have any C-naughts, then like theoretically you shouldn't be able to pass that data along. So yeah, that's basically it. Lack of C-naughts and very few parameterized gates were the worst performing ones.
Any other questions? All right, if not, let's thank the speaker again. Thanks, Thomas, for giving this wonderful presentation. Yeah, and that wraps up for our presentation session today. And just to let everyone know, there is a Unitary Fund. I think it was a workshop or a talk right after this, and please join us and stay connected, and hopefully we can have some collaboration in your research for all of you in the future. And thanks again for joining. Right. See you guys later. Okay.
Thanks for coming.